I would check the bin and see what other homework assignments are similar to that, and then you can figure out what it is. Talk to all your other friends that didn't turn it in yet. They probably still have it. But if you need to look it up, you can look it up in Homeroom or something. All right, so we're starting at the back of the packet, which means the one that I'm showing you right now is the hardest version of these last four. So it's okay. It's going to be a little weird at first, but it's the hardest version, okay? Because we're starting at the back. Okay? So as we go further, it'll get easier. So what kind of center must this be? In center, because it's inscribed triangle, or inscribed circle in a triangle, right? Now, that means this and this must be what? Radii. Good. So if that's a radii, G to anywhere on the circle will be 5, which is why they're congruent, right? So G to F will also be what?
5.
Good. No proofs required. We're just applying it, okay? We know that all radii, when you measure to the sides of a triangle, right? When you measure from G to the side of the triangle, you measure perpendicular, right? And the point is that G is equidistant to every side, right? So if we measure perpendicularly, this is a 90 degree, and this is a 90 degree, right? So you get those for free. So let's solve some problems. Well, let's find y first. Y is part of a 90 degree triangle, right? Is it the leg or the hypotenuse of that triangle?
Leg.
It's a leg, right? And we know it's not the hypotenuse because the hypotenuse is always across from the 90 degree, right? So GB is the hypotenuse in this. So if I knew what the hypotenuse was and I knew what one of the legs was, I could use Pthag to find y, right? So I need to know what that hypotenuse is. Well, luckily, I have another triangle over here that shares that hypotenuse, right? And I already know 2 of the legs, don't I? So I can use Pthag to figure out that hypotenuse. So I'm going to do that. Leg is 5, so I do 5 squared. Other leg is root 21. You're like, oh, God, that looks awful. It's not. Plus whatever GB is squared, right? Because that's the hypotenuse. So we cool with that? So far, so good? All right. 5 squared is 25. What's root 21 squared? 21. That's it. That's it. Roots and squares cancel. What's 25 plus 21? So GB must be whatever the root of 46 is. Sounds like a fun place to drive. So this right here is root 46. Wait. This triangle and this triangle. Hypotenuse are both 46 for both, and their legs are both 5. So by hypotenuse leg, they're congruent, aren't they? So that means y is root 21. Now, if you didn't see that, that's fine. Just do Pthag, right? 5 squared plus we don't know squared. That's y, right? It's a leg, so it goes here. Don't assume just because it's the variable, it's the hypotenuse, right? Don't write it over here. Do you guys see that? I swear to God, you're going to make mistakes on this. So are you paying attention? These are both legs, right? So if I didn't know what this was, right, I did it by congruent triangles, right? But if you didn't know what that was, you do Pthag, right? Yeah. Those are both the legs of the triangle, so they go here. A lot of you guys are going to be like, oh, variable, stick it here. No, the hypotenuse goes there. And it's squared, right? So we have 46 equals whatever y squared is plus 25. If you subtract, you get y squared is 21. Or not 21. Yeah, 21. And when you root it, you get root 21. Cool? So you can solve it like that, or you can solve it just by saying, oh, they're congruent, right? If that's root 21, this should be root 21. Again, this is the hardest version of this problem I can give you. Are you feeling somewhat okay with that? I set the bar low because I thought, you know what? This is a valid thing that you should know how to do. And it's easy to do if you know your crap, which is the kind of stuff I throw in my quizzes, right? If you don't know your crap, there's no way you'll solve any of this, right? So, know your crap and you'll be fine. But the problem is that usually when I set the bar low, you don't just step over it like you should and say, yeah, I win. You usually trip over it. Okay? I think I'll set the bar low. It'll be really easy to walk over and you trip. Don't do that. Okay? Yeah, Noah.
So, couldn't you move on like triangle GDB congruent to triangle GEB?
Yep, by hypotenuse leg, right? And then you just get root 21 for free. Yep. That's what I did the first time. If you don't see that, you can just do math, right? Yeah. Yeah, we can, right? These two triangles are going to be congruent. How do we know? by hypotenuse leg, right? They share the hypotenuse, right? So that and that shared, that and that, right? So if that's 12, this must be 12. If you didn't know that, you could do 5 squared plus 12 squared because of the legs and get the hypotenuse. 25 plus 144 is 169. What's the root of 169? 13. So if that's 5, 12, and 13, and this is 5 and 13, that has to be a 12. Yeah.
Sorry, I kind of how did you get the 5 from the GM?
Because anywhere from the center of a circle to the outside of the circle is 5, right? Because it's the radius. Cool. And I know that's 90 because when we measure to the side of a triangle, it's always going to go at 90.
I got all that.
Cool. Okay, that's fine. That's it. That's it. 13. How many triangles do you see?
3.
2.
How is that a triangle?
There's a big one, ABC, and a little one, ADE. That is not a triangle.
That's why I was
I just started counting the points on the page.
There's 2?
You taught
There's
us
2.
wrong.
2, but how do you see the CEDB as a triangle?
It's not.
I know. That's what I'm confused.
Oh, you're saying they. Okay, got it. All right. Yes. I've accepted this as true. It's like someone goes, "Oh my God, the sky is blue," right? It's like, why? What? Right? I'm curious why we're talking about this. Yes, I know. Okay. All right. So
What?
by cap, these are congruent, right? And they share that angle A.
It's actually gray right now.
And these are congruent by cap. This might help you to label this. If you want, because these triangles are similar, you can write the similarity statement. You don't have to. But triangle ADE is the small one, right? And by double angle, it's similar to the big one. A goes with what in the big triangle? A. D on the small triangle goes with B on the big triangle, and E on the small goes with
C.
Okay, so if that helps you match stuff up, right, we're going to do CSP. If not, you can just be like, look, between blue and green is 9. Between blue and green is how much for this side? 12. 3 is not a triangle. It's going to happen to you. It's going to happen to you. So we know AE goes with AC, right? So 9 goes with 12. AD and AB. AD is this. That's X. AB is what? How long is that?
5. AB.
Yeah. X plus 5. It's segment addition. That's it. It's going to be okay. It looks weird, but it's going to be okay. It's going to be okay.
I know, I was just wondering how to
Good. And then ED and BC go together, 12 and Y, right? Don't goof up your order, right? If you start with the small triangle on top, make sure you keep with the small triangle, right? 9, X, and 12 on top. Big triangle stuff on the bottom. 12, X plus 5, and Y. Don't goof that, okay? So, again, you don't have to write that, but it can help, right? So now we know 9 over 12 reduces to 3/4. So all of these relationships are 3/4. So let's solve this one. How do you solve a problem like Maria? We want to get X on its own, basically. Well, if this was a 2 under here, wouldn't you multiply it over? Well, it's not a 2. It's this. We're just going to multiply it over still, though, right? Now, how many terms are here? 2. 2 terms, right? See how they're separated by a plus or minus? So that's 2 different terms. We have to wrap that in parentheses if we want to move it over, okay? So what I get is X plus 5 times 3/4 equals X. I just moved it over by multiplication. You cool with that? I moved it over by multiplying. We cool? Nope. I'm taking this. Oh, sorry. 9 over 12 reduces.
Yeah.
So I'm taking this, and I'm doing multiplication. Do you know where I got this from? Okay, similar triangles. 9 goes to 12 as X goes to X plus 5 as 12 goes to Y. I just did CSP.
Okay.
Okay, better? Good question. All right, so now I can distribute. Something like that. I can subtract 3/4. What's 1x minus 3/4? X. How much is left over? 1x minus 3/4 of x. 0.25, a quarter of x, right? How do I get rid of the quarter? I divide by a quarter or multiply by the reciprocal. Multiply by 4. What happens when I multiply both sides by 4?
Cancel.
I get 15 equals x. Okay. There are other ways to solve that. If you want, you can just multiply this over from the beginning and then not reduce. That won't have you have fractions, actually. It'll be a little bit nicer. It's up to you. Yeah?
Wait. Yeah.
Okay, so x is 15. Now let's find out what y is. Well, we know we need to flip this, right? To get the variable on top, it'll be a lot easier. So I'm going to write y over 12 equals 12 over 9. Are we cool with that? I just flipped those two. Having the variable on top makes it easier to solve. What do I do to solve this? Multiply by 12. So y equals 12 times 12, which is 144. And I divide by 9. If you're clever, you won't multiply 12 by 12. You'll write it like this. Right? Totally valid, right? What's 9 times, what can I break down 9 into? Something times something. What?
3 times 3.
I don't know 144 divided by 9. But I know 12 divided by 3 and 12 divided by 3. What's 12 divided by 3?
4.
So I have 4 times 4. Right? That's clever, huh? So y is 16. I love that. I wish you guys had algebra with me. How to play with numbers, guys. Once you learn that, everything else becomes easy. I wish you had algebra with me. So 144 divided by 9, I don't know. But another way to write 144 is 12 times 12. And another way to write 9 is 3 times 3. Well, when we divide, we just have to divide one term. How many terms are here? 1, because it's not separated by a plus or minus, right? So you can choose to divide this by 3 and then this guy by 3. It's the same thing, right? It's dividing 144 by 3 twice, dividing it by 9. If you had algebra with me, it would make a lot more sense. Sometimes simplification isn't simpler. Yeah.
Doing the fourth thing. 15 is not 3/4 of
15 is 3/4 of 20. Whole thing is 20. That's not a triangle.
Right.
It'll happen to you. Yeah.
How did you? I didn't see how you got x plus 5 times 3 over 4 equals x to like the next step.
So I took this right here
Not that. It's still.
and I multiplied over. I distributed the 3/4 x, or 3/4. 3/4 x, 15 quarters. If you have 3/4 and you times it by 5, you now have 15 quarters. Right? Think literal quarters. I have 3/4 and I times it by 5. I now have 15 quarters. That's how fractions work. You multiply in the top, divide in the bottom. I wish you had algebra with me. All right, so then I subtracted 3/4 and got 1/4 and times by 4 to both sides. Worked out nicely. It's actually easier not to simplify this first because then you get 9 times x plus 5 equals 12x. And you get 9x plus 45 equals 12x. And when you subtract 45, you get 3x, and you divide by 3, and you get 15. Sometimes simplification isn't easier, which is why I don't like calling it simplifying. Reducing, sure. Simplifying, well, sometimes it's not, right? This guy, thinking of it in a complex way, actually makes it easier. Let's look at 12. What kind of center must that be? Orthocenter, because these are orthogonals. If I have the orthocenter, that's going to create a lot of similar triangles, right? Because I have vertical angles here, right? Is that a triangle? No, so they're not going to be similar. If I drew in the last one, it would be, right? It'd break it up, right? But I don't need that. Ooh, that would actually be an interesting way to solve. It'd actually be easier, but that's okay. We're going to pretend you won't see the big brain play. All right, so first of all, how do we solve a problem like Maria? How do we find out what V is? P-vag, right? It's a right triangle. When in doubt, if it's a right triangle. If it's a right triangle, I swear to God, right? P-vag is something you should always look for. Just like if it's a right triangle, you should look for HL. Right. So if that's 3, and this is V, and this is 5, which one's the hypotenuse? Which one's the hypotenuse of this guy? 5, right? So it's going to be 5 squared on one side equals V squared plus 3 squared, right? Don't assume that V is the hypotenuse. You will. Don't. Have you tried not?
Isn't the hypotenuse just the longest side?
It is. It's always across from the 90-degree angle. Some people might think that looks longer, right? You have to be careful. It's always across from the 90 because the bigger the angle, the bigger the opposite side, right? And 90 is the biggest angle you can have, right? If it's not obtuse. If you have one angle that's a 90, that's the biggest angle you can have, right? It's always the biggest angle in the right triangle is the 90. So the biggest side is across from it. So 4. It's a 3, 4, 5 right triangle. If you know your special right triangles, 3, 4, 5 pops up all the time. So does 5, 12, 13. All right, this guy. We know those two are similar, right? By double angle. If it helps, you could write the similarity statement, or you could just go off the angles, right? You could write that EA is going to be similar to this, right? We could match up the letters, right? EAG will be similar to DBG, right? You could write that in the new CSP. I'm going to be quick. Between the red and the green angle is 3, right? On the small triangle. What's between the red and the green angle in this triangle? 7. 5 is between green and blue, otherwise known as the hypotenuse, right? What's between green and blue here? So 5 goes with X. 4 goes with what? Well, this side, we don't know. We don't care about it, though, so who cares? How do you solve a problem like Maria? Isn't it hard when the variable's on the bottom? Then flip it. As long as you do it to both sides, that's algebra. How do you solve a problem like Maria? Multiply by 5, right? What's 5 times 7 divided by 3? What's 5 times 7? What's 35 divided by 3? Thank you very much, Chloe. Sometimes it do be like that. That's okay. Most right triangles are going to have weird side lengths. That's why it's special when you find perfect numbers like 3, 4, 5 or 5, 12, 13. Okay? It's fine. You're done. You're not going to mess with that anymore. Now, how do we find x and y, or y and z? You only need these triangles. Do you see similar triangles? What angle does the big triangle ADC share with AGE? They share A. They're similar. So let's match up the hypotenuse of this guy with the hypotenuse of this guy. 5 in the small triangle goes with the hypotenuse of the big one, right? Between blue and green is 5. Between blue and must be green is what? Try again. Blue and green is 5. Between blue and green is what? Z plus 4. Very good. It'll happen to you. It's the whole thing, right? Now let's match up this guy. Green and red on this one is 3. What's between green and red on the other one? Between green and red. Green and red. Why? I ask the questions. What about between red and blue? Well, that's 4. Between red and blue on this triangle is what? 12. Do you see it? It'll happen to you. This is not a triangle. All right, so let's solve this one first. We can reduce if you want and flip. What's 12 divided by 4? 3. So we multiply by 3, or we multiply this side by 3, right? And we get y equals 9. Right? 3 here, multiply by 3, it's 9. Y is 9. Let's find out what z is. Another way to do this is to call this a different variable, like q, and then find it and subtract 4, and you get z, right? So you could just call that q if you wanted, and then subtract 4 from it and get z. It's up to you. I'm going to do it this way. Z's on the bottom, so I'm going to flip it. Z plus 4 over 5 equals 12 over 4, right? Cool. That's 3. How do I solve a problem like Maria? That reduces to 3. Go.
Multiply by 5 and subtract 4.
Yep. Multiply by 5, and now it's gone. And then subtract 4, and then z is on its own, right? So what's 3 times 5? Minus 4 is? Z is 11. Make sure you understand this. I've given you fair warning. 11. You're welcome, Jess. I answer everybody's questions. All right, so what kind of segments must these be? Medians. What do we know about medians? They're what to what? 2 to 1 and vertex to midpoint. So this is a midpoint. This must be a midpoint. This must be a midpoint because G is the medicenter, right? Cool. What else do we know? 2 to 1, right? So if this is 5, that's the small side. How's the big side? What's it going to be? 2 to 1, double in half. Yeah.
So we can just say that one side is the small side if
You know it's the small side because vertex to midpoint, or sorry, centroid to midpoint or medicenter to midpoint is always the smaller side. And we kind of proved that earlier, right? Similar to this. This is smaller than this, which means that's smaller than this, right? Okay, cool. So x is 10. What's y going to be? 13. I'm going to write this in because to find out z, you have to be clever. Big brain play. Yeah.
Okay, kind of unrelated, but how do we know that that's exactly double 5?
It's always true for medians. They divide themselves into half and double. Always. We proved that like 4 weeks ago. We didn't call it that at the time because we didn't know what a medicenter was, but we ended up proving it. It's just a property of the medicenter. Yeah.
Are triangles, what is the middle of that one?
What are you talking about? This guy?
A through C.
Oh, A, Z, C. That's what we got to find?
That's Z.
Yeah, Z. The whole thing is Z. The point there, is that what you want to know? It doesn't matter. You can call it M if you want.
So are the triangles?
So they have the same height, so we should use, like, is it Cephas theorem?
God damn, that was good. Guys, these two triangles have the same height. So their bases should be proportional to their area. Well, the area of these two triangles is actually going to be the same because they have the same base and the same height. Right? They have the same base times the height divided by 2. Right? That's good. That's good. But that's not going to help us. Because I actually need to know the numbers. Oh, yeah. Isosceles triangle theorem converse. Do you guys see that it's isosceles? So those angles are the same. Now, more importantly, if a point is equidistant from the endpoints of a segment, that point must be on that segment's. So this is a perpendicular bisector. So we got to write triangles. What are we going to do to figure out this length right here? Pythag. 5 squared plus something squared equals 13. What's a special right triangle that has 5 and 13 in it? I said it multiple times already. 5, 12, 13. You could do Pythag to figure it out. Those are both legs, right? This is 12, which means Z is? Yeah. I love that. I love that. I went out of my way to make sure those are both congruent just so you could do it. G has to be on the perpendicular bisector. Well, if it's already on the bisector, it must be 90 degrees, right? That's good. That's good.
So the goal of all these problems is just to find what every letter equals.
This one's actually easy, but if you want to see it, I can do it. It's a lot of writing. It'll take up probably all of our time. Do you want to see it? Parallel here, parallel here, parallel here, and we make a bigger triangle, right? Then we do medial triangle theorem. You can draw this symbol for medial triangle theorem if you want, okay? Right? Says that these will be congruent, right? The opposite sides will be congruent and parallel. So like this and this are congruent and parallel, right? And we do it for all of them. We write that all down. And then we draw an angle bisectors, right? Boop! And we create alternate interior angles here and here. It's hard to see it, but it's there. Okay. And then we win. Step 1, draw parallels. Step 2, medial triangle theorem, say things are congruent, right? Step 3, draw on your perpendicular bisectors. Step 4, alternate interior angles. Win. You want to see it or no? It's okay if you do.
Do it fast.
Do you want me to write it all out or just do the drawing?
I just want to be able to see it.
Just do the drawing.
Try have a finished one.
I already have a finished one, and I have the video.
Yeah,
Watch the
I'll
video.
watch
If you have questions about how it's done, because if you have questions about how it's done, I won't answer that in the video. You know what I mean? Like, you have specific questions. Otherwise, just watch the video, right? Yeah.
Great. I'm still on 11. How did you get through D 12s?
5 squared plus x squared, let's call that x, okay, equals 13 squared.
Okay.
P-Thag, good question. And I know 5, 12, 13 is a special right triangle, so I just cut to the chase. 3, 4, 5, 5, 12, 13. Those are the big special right triangles you got to know. There's also one with 17. I don't remember it, though. You want to see 9 or no? Perpendicular bisectors? Are perpendicular bisectors Cevians?
No.
No, because they're not vertex to opposite side, right? Here's an example of a perpendicular bisector, right? Is that a Cevian? No. So are we going to use Cephas theorem? No. We're going to draw 2 of these, and they're going to intersect at some point, right? We can assume 2 intersect at a point. 2 lines intersecting at a point happens all the time. We know they're not going to be parallel. Can you have a triangle with 2 sides that are parallel across from each other like this? 2 adjacent sides? No way. In fact, you can't have any sides parallel. Wouldn't work, right? Imagine these 2 sides are parallel. Well, then you don't have a triangle anymore, right? So these are going to intersect. We're going to prove that the last one must have to go through this intersection point. So we're going to say let this exist and this exist. Okay? So let DKE and EKG exist. Whoops. Now, DKE and EKG are perpendicular bisectors of what sides? DKE is the perpendicular bisector of what side? CDA. Do you see how it's perpendicular with this side? So I'm going to write that. I'm going to call it ADC. Cool? Right? What is EKG, the perpendicular? Sorry, not EKG. It's FKG. Letters are hard. FKG. What is it the perpendicular bisector of? CFB. This side, right? It's perpendicular with this side. Cool? Now, we know they intersect at K because they both share K. Right? Now I'm going to prove the last one has to go through K. If I were to draw it in, it would have to go through there. Okay? So, here's how I'm going to do it. Perpendicular bisector theorem and its converse. Because we're dealing with perpendicular bisectors. This is hard. Right? You're going to use perpendicular bisector theorem and its converse because we're talking about perpendicular bisector theorem. When we do the angle bisectors one, when we do the angle bisectors one, we'll use angle bisector theorem. TAB, right? Triangle angle bisector theorem. That makes sense. We're talking about angle bisectors. So, how do I know that K is the same distance from C and B? We're talking about perpendicular bisectors, so what theorem are we going to use? Thank you. Which says that if it's on the perpendicular bisector, then it's equidistant to the endpoints, right? If it's on CB's perpendicular bisector, right? And it is, then it should be equidistant to CB's endpoints. If it's on CA's perpendicular bisector, which it is, then it'll be equidistant to CA's endpoints. That's perpendicular bisector theorem. Now, here's the magic. The converse of perpendicular bisector theorem says, if you're equidistant to a segment's endpoints, then that point must be on what? Nope. If a point is equidistant to the endpoints of a segment,
Oh, perpendicular, right?
it must be on the perpendicular bisector. If a point is equidistant to the endpoints of a segment, it must be on the perpendicular bisector, right? That's perpendicular bisector theorem converse. So is K equidistant to A and B? Yeah, then it must be on AB's perpendicular bisector. So by perpendicular bisector theorem converse, K is on AB's perpendicular bisector. Well, if it's on AB's perpendicular bisector that I've yet to draw, and it's on AC's perpendicular bisector, and it's on BC's perpendicular bisector, then they must all intersect there, right? So we win. Whoops, triangle. That's actually one of the easier ones. We use perpendicular bisector theorem because we're talking about perpendicular bisectors, which says that if it's on a perpendicular bisector, then it's equidistant to the endpoints. If it's on a perpendicular bisector, it's equidistant to the endpoints. The converse is, if it's equidistant, then it's on the perpendicular bisector. So it must be on this guy's perpendicular bisector. And if it's on this guy, and that guy, then they must intersect there, which means they're concurrent. Questions on that? No? Erica? You all right? Okay. Speaking of perpendicular bisector theorem and its converse, do you know how to prove it? You want to talk about it or no? How do you prove that D is equidistant to A and C given this diagram? Zayden.
Create a triangle, have shared sides, and then
By SAS, the triangles are congruent, which means these sides are the same. And if the sides are the same, isn't D the same distance from A and C? How do you prove the converse? That if it's the same distance, then it's on the perpendicular bisector. This one's a little more complicated. What do we have to draw in? We drop a 90 degree, right? Allowed to do that whenever. And then we prove by HL, right? Hypotenuse leg, that the triangles are congruent. And if they're congruent, then these sides are the same. And if these sides are the same, isn't this blue line a perpendicular bisector? So by definition, we win. Enough said. Angle bisectors are concurrent. What theorem do you think we're going to use? The triangle angle bisector theorem, right? Because we're talking about angle bisectors. Are angle bisectors Cevians? Yes, so we will use Cephas Theorem's converse. We will, to prove that they're concurrent. So first off, what is triangle angle bisector theorem? It's this. If you got a triangle and you got an angle that's bisected in it, that makes sense. The triangle angle bisector theorem. A triangle with an angle bisector in it. How do they think of this stuff? Then you get this. Always. Here's what I'm going to do. I'm going to draw on an angle bisector. Okay? I'll call it something like AE. Why did I skip D? I don't know. Now, doesn't that cut the triangle into two sides and two bases? So therefore, AC over AB will equal CE over BE. Do you see what I'm doing here? I'm going to do that for all the sides. Do that for all the sides. Okay? So we're going to say let AE exist. And then it cuts these angles into equal, right? So I'm going to say CAE. Congruent to angle BAE. Bay. Now, I'm going to keep doing that for all the sides. After I do that, I'm going to say by tab theorem. Let's do this as we go. The two sides that I cut are CA and CB, right? Sorry, CA and AB. So I know AC over AB is going to equal, what are the bases that go with that? EC and EB, right? In that order, AC goes with CE and AB goes with BE. I'm going to do that for all my angle bisectors, okay? So I'm going to draw another one in. Call it BD, since I didn't use D earlier. That cuts it into two angles, ABD and CBD. Nice. We did it, boys. Cool. Now, doesn't that mean I have triangle angle bisector theorem here too? Right? AB and BC are going to go together. AB and BC cut it into two bases. AB gets AD, and BC gets CD. Are you following me on that?
Yes.
Yeah. Okay. Nancy, I like your hair.
What about my
I like it. I used to have a student in Sandwich, I believe, and she was wearing what I thought was a dress. And I said, "Oh, I like your dress." Instead of, "Oh, thank you." You know what she said? "It's a skirt!" You right. You right. You right. I'll think next time. All right. So, not assuming they intersect, right? We're going to prove that they do. If you draw it through there, it doesn't matter. So I'm going to say let CG exist. We'll call it triangle ACG, or sorry, angle ACG, congruent to angle BCG. Now, can I do the same thing, right? These sides go with these bases. So side AC and side BC will go with base AG and base BG. Make sure you don't goof those up, right? These sides go with these bases, right? X goes with A, Y goes with B. You cool with that? All right. So now I'm ready to set up Cephas Theorem, right? I'm going to go around the triangle, okay? It's time to go around the triangle. Let's write that down. It's AG. What's next? I'm going around the triangle. What's next? BG, alphabetical please, times what? BE, letters are hard, and CE times CD times AD. Now I'm going to prove that equals 1, because if it equals 1, they're concurrent, right? Well, what is AG over BG? I know that. What's BE over CE? It's this but flipped, right? So be careful, flip it, AB over AC. What's CD over AD? Flip it, but we know it, right? It's BC over AB. And what happens? What happened? What happened? So if they equal 1, they must be concurrent. What theorem is that? Converse, right? Cephas Theorem says if they're concurrent, then you get 1, right? The converse says if they're 1, you get concurrent. By Cephas Theorem converse, the angle bisectors of triangle ABC are concurrent. No, can I turn the page now? Okay, good. There's no point in me writing that, so I just... How do you prove it? Draw your parallels. Boop. Extend your thing. Alternate interior angles, yep, here and here. Vertical angles here and here. These two triangles are similar. I know this and this are both Y because isosceles triangle. Do CSB. A over B equals X over Y. Sorry, X over Y. AB, XY. I win. You want to see the medians one? Our median Cevians. Yes, so we're going to use Cephas Theorem's converse eventually, right? So we draw 3 medians in. Boop, that's a median. Boop, that's a median. Boop, that's a median. And then I go around the triangle because I'm basically done, right? Because I know A, D is the same as BD, right? And that's what I'll do my substitution in, and they'll all go away and become 1. Are we good with that? Watch it on the review if you need it. Proof by contradiction. What theorem is this? Cephas Theorem. Converse. So what we're going to do is we're going to assume the opposite, just like the diagram does, right? See how the diagram assumes they're not concurrent? That's wild. It's wild. So we're going to assume that if they're not concurrent, there must be a line that is, right? Whoops, we'll call it J. Okay?
Yeah, you can't use that.
Now, if this is concurrent by Cephas theorem, this over this times this over this times this over this will equal 1, right? But here's the problem. We already know that this over this times this over this times this over this will equal 1. So this over this will equal this over this. And that's a contradiction. How can you divide up a segment into this and have it be equal to this and that? You can't. Not in the same order anyway. Right? This length can't be the same as that length. So it's a contradiction. Therefore, our assumption that they were not concurrent must be false, which means they are concurrent. If you're seeing this for the first time, you're like, oh God, what? If you're seeing it for the 5th time, you might be like, okay. You're good. You're good. What theorem is this? Cephas theorem, right? Because they're concurrent, and we're going to prove they equal 1, right? Before we can go around the triangle and prove they're 1, what we have to do is the height thing. Remember that? If they have the same height, then their areas are proportional to their bases. So this triangle and this triangle go with A and B. But so does this triangle and this triangle, which means when you subtract them, this triangle and this triangle go with A and B. And we do it for all of them, right? And then we set up Cephas theorem, right? And prove it equals 1. This is actually very doable. Ooh, we forgot about this one on the back. I don't think anyone's done this one today. G is the circumcenter. I forgot 15 was even on here. If G is the circumcenter, what kind of lines make the circumcenter? Good. So if these are the perpendiculars, they must also be the bisectors, right? So if that's 6, this is 6. And these are equal, right? Oh, and also, aren't these radii of the big circle? So they're all congruent. So those are all 10. Do P-Thag. See you tomorrow. Yes. I love your scrunchie and how it matches your shirt. It's a hair tie. Are you both getting passes? Are you both in the same homeroom? Okay.
Hey, Mac, where's the bin for late work?
You're good.
Alright.
Brains. Kill this test tomorrow, Danny.
How was the track meet? Did you?
It's cool. I think we're going to switch turn-in days to Mondays because no one ever remembers to turn stuff in on Fridays. Even though you're turning in a quiz. Right? No one ever thinks, oh, I should also turn in this. I thought it would work. You know what happens when you think. You get disappointed.
I don't know what the warm-up is.
Oh, that's right. How would I recommend going about this? Pardon me. Loving the style today, Macy. Alright. First hour, third hour. Third hour is homework that I do over the weekend. That's the non-major. See if you can find that one. Does that make sense? Oh no. Rip. Apparently the tape is weak enough where it'll fall off the wall, but it's strong enough when it falls on the floor without anyone pressing it down.
Can you make sure you answer that question I sent, please?
Yes.
Thanks.
Yeah, I didn't know you sent a question.
Through the MEA, remember you asked me that,
Oh, okay.
Yeah.
How do I answer if I'm staying the same?
there's no education change.
Oh, there
That's
was?
the first
Oh, I'm
choice,
sorry.
yeah?
Okay, thank you, Connie.